Namaste one and all. So today we will be looking at a new concept, electric field and field lines. So you know that when two charges come nearer, there will be some interaction between that. It may be either attraction or repulsion. So is there something which is associated with a single charge? So let us now look at this. A single charge capital Q we are considering here produces something called as electric field everywhere in the surrounding of it. So now you came to know that if there is single charge, it produces some electric field around it. So a single charge produces an electric field around it. So when another charge, small q, the name of the charge is small q, is brought inside the electric field of this capital Q, it experiences some force. So let us consider another charge plus q, which is small q, is brought inside the electric field generated by this capital Q charge. So this charge experiences some force. So since this is positive, this is also positive, this experiences repulsion. The charge which you are considering here, that is small letter q, is of 1 coulomb. So you can call this as test charge. So when you bring a test charge within the electric field of another charge, this test charge experiences some force. So that itself is called as electric field. So it can also be said that electric field is nothing but force per unit test charge or force per unit charge. So how do you calculate this electric field? So now you know that there is a charge which is producing electric field surrounding it. Okay. So how do you find this electric field at any point? So the formula for this is given by electric field is equal to K into Q divided by R square, where K is equal to 9 into 10 to the power of 9 and Q is the charge which is producing the electric field and R is the distance at which you are interested in finding the electric field. So this gives you the electric field value. It gives only the magnitude. But in order to find the direction, we need to know the field lines. Now if we consider the electric field line, for a positive charge, the electric field will be pointing outwards. And for the negative charge, the field lines will be pointing inwards. Always remember, for positive charge, it will be pointing outwards, and for negative charge, it will be pointing inwards. Now let us consider a problem to understand this concept properly. So let's consider 2-point charges Q1 and Q2 of magnitude 10 to the power of minus 8 coulomb and minus 10 to the power of minus 8 coulomb, which are placed 0.1 meter apart. Find the electric field at point A and B. So what they are given is there are two charges Q1 and Q2. The magnitude of Q1 is 10 to the power of minus 8, so it is positive, and the magnitude of Q2 is minus 10 to the power of minus 8, so this is negative charge. So the distance between them is 0.1 meter. So you need to find the electric field at position A and B. So first find the distance of the point from the two charges. The distance of A from Q1 is 0.05 meter and the distance of A from Q2 is 0.05 meter. Similar distance of B from Q1 is 0.05 meter and the distance of B from Q2 is 0.05, 0.05, 0.05. So total is 0.15 meter. And now you need to know the electric field lines. So since this is the source or positive charge, electric field lines will be outwards. And since this is negative, the electric field lines will be inwards. Now let us find the electric field at point A. So there is nothing but K into the charge which is producing, that is Q1, divided by distance, that is 0.05 square. Next, the electric field due to Q2 is plus K into Q2 divided by 0.05 square. Now you observe here, the positive sign indicates, what does it indicate? So at point A, the direction of this is towards right. So just look at the arrow, it is pointing towards right. The arrow due to Q1, it is pointing towards right, that is moving outwards. And again the red, that is the red arrow, it is also pointing towards right. So since this is a negative charge, electric field has to be inverse. So both the arrows are pointing towards the right side. So we just need to add the arrows. So that would be k into q1 divided by 0.05 square plus k into q2 divided by 0.05 square. Now substitute the value for k. It is 9 into 10 to the power of 9. q1 is 10 to the power of minus 8. q2 is minus 10 to the power of minus 8. So get the answer as 7.2 into 10 to the power of 4 Newton per coulomb or volt per meter. Now let us consider a point B and let us try to find the electric field at point B due to Q1 and Q2. So the distance of B from point Q1 is 0.05 meter and the distance of B from Q2 is 0.15 meter. So the value is K into Q1 divided by 0.05 meters, K into Q2 divided by 0.15 meter square. Okay. So now you observe the sign over here, it is negative. Why is it negative? Look at the arrows. So the arrow due to Q1, so it is pointing towards left. So because the Q1 is source, so the arrow should point outwards, and the arrow due to Q2, you just look over here, it is pointing towards right. So one arrow is pointing towards left and the other arrow is pointing towards right. So we need to subtract one from the other. So we need to subtract this blue color arrow with the red color arrow. So that is the negative sign. So this arrow direction, that is electric field line direction, gives you the direction and the formula gives you the magnitude. So the answer would be 3.2 into the power of 4 Newton per coulomb or volt per meter. So now you are aware of how to calculate the magnitude, that is electric field magnitude at any distance from any point charge along with its direction by knowing its electric field lines. I hope you have understood this concept. Thank you. Simulation version of the electric field and electric field lines which you have studied right now. So first let me consider a positive charge. So this is a positive charge. So if you consider the positive charge, so it will be having electric field around this. So let me try to find the electric field value at some point. So let's consider at this value, this position, what is its value? So it is 3.39 volt per meter. So how do you tell that it is 3.39 meter? So you know, according to the equation, the electric field at any point is given by E is equal to K into Q divided by R square. So the value of K is 9 into 10 to the power of 9. So the value of Q is 1 nanocoulomb. So it is into 1 into 10 to the power of minus 9 divided by the distance from this charge to the point where we are calculating the electric field. So let me consider the distance. So the distance of this is 161 point, so that would be 161.3 161.3 into 10 to the power of minus 2. So this would be, so the value of R is 161.3 into 10 to the power of minus 2 meter square. So that gives you approximately 3.4 volt per meter. So with the help of this equation, we'll be getting the electric field magnitude. So the direction is given by, the electric field lines. So if we look over here, this is your source or positive charge. So the electric field lines will be pointing outwards. So look over here, it is pointing outwards. So it is pointing outwards. So if we consider the electric field lines of a positive charge, it will always be pointing outwards. So at different points, you'll be having different electric field values. When you go away from the charge, the electric field is decreasing. Look over here, it is 1.450. When you take the electric field closer, that is electric field value closer to the charge, would be maximum. That is at shorter distance from the charge, you will be having higher value of electric field. As you go away from the charge, the electric field value would be decreasing. Now let us consider the case of a negative charge. So let me take this, instead of positive charge, let me take the negative charge. So now let me consider finding its value. So again we'll be making use of the same equation to find the electric field value, K into Q divided by R square. The value of K is 9 into 10 to the power of 9 into the value of Q is minus 1 into 10 to the power of minus 9 divided by distance. So we need to calculate the distance. So let me take here. The distance is 126.2, so it would be 126.2 so the distance is 126.2 into 10 to the power of minus 2 meters square. So this is approximately minus 5.65. So we can take this as 5.65 volt per meter. So here the negative value indicates that this is a negative charge. So its electric field line is pointing inwards. So electric field line is pointing inwards because this is a negative charge. So look over here, the electric field line is pointing inwards because it's a negative charge. So the electric field line will be inwards for negative charge and it will be outward for positive charge. So similar to the positive charge, as you go nearer to the charge, the electric field value will be higher. As you move away from the charge, electric field. So let us consider another example of electric field. So here an electron falls through a distance of 1.5 centimeter in a uniform electric field of magnitude 2 into 10 to the power of 4 Newton per Coulomb or volt per meter. The direction is reversed, keeping its magnitude unchanged, and a proton falls through the same distance. Then we need to compute the time taken for fall in each case. So what they are saying is, so there is a positive charge and there is a negative charge. So you know that electric field line will be going outward from the positive charge and will be inward for the negative charge. So the electric field lines are moving from positive to negative. So this is your electric field line from positive to negative. Now you are keeping a negative charge in the electric field. So what happens? So since this is negative, it will be attracted towards positive charge. So this would be repelled by the negative charge. So it starts falling towards positive charge with some acceleration. So it moves towards or falls downwards with acceleration towards positive charge. So the height through which it will be falling is given by 1.5 centimeter. So the time of fall is given by the equation 2 into h divided by acceleration of this electron or negative charge. So the force on the object which is falling is given by force is equal to mass into acceleration. So the mass of an electron into acceleration of the electron, and force on the negative charge electron due to electric field is given by E into E, where E is the electron and capital E is the electric field. So we can equate these two since both of them are forces. So by equating them, we'll be getting the acceleration. Acceleration of electron is equal to E into capital E electric field divided by mass of electron. So substitute that over here. So this is your equation. Now you can substitute the values, where h is the height through which it is falling. So it is equal to 2 into 1.5 centimeter, 1.5 into 10 to the power of minus 2. And mass of electron, as you all know, it is 9.11 into 10 to the power of minus 31 divided by E electric charge, that is 1.6 into 10 to the power of minus 19. And electric field E, that is uniform electric field E, is given by 2.0 into 10 to the power of 4. So when I calculate that, the value turns out to be 2.9 into 10 to the power of minus 9 seconds. So this is the amount of time taken by negative charge to fall in the electric field which is uniform. Now let us consider the other case. Now we are just reversing the magnitude. So now the bottom is taken as negative and the upper side is taken as positive. Now the electric field line will move from positive to negative, since the electric field moves outward of positive and inwards to the negative. So this is the direction. So now we are placing a proton, E plus. So this is positive, it is a proton. So this is positive and the upper one is positive, it will be opposing force, and bottom is negative, so that will be attractive force. So this would be falling towards negative, that would be downwards. So this is the direction. So the falling time is given by the same equation as that of electron, but here instead of mass of electron, we just need to consider the mass of proton. So you know that mass of proton is 1.67 into 10 to the power of minus 27. So if you substitute this, so the fall time is given by 1.3 into 10 to the power of minus 7 seconds. So if we compare these two, although the mass of the proton is very higher when compared to the mass of electron, so proton takes longer time to fall when compared to electron, that is negative charge. So that is, we are telling to say that although the mass of proton is heavy, it falls slowly through the same distance, which is contrast to the falling under gravity. In gravity, what happens is both the objects will fall at the same time, whereas in case of electrostatics, so the proton, although this is heavier, it falls slowly when compared to electron, which is lighter. I hope you have understood this concept clearly. Thank you. Thank you for watching the video. I hope you have understood the concept. So to know whether you have understood the concepts better, you need to answer the quiz. The link for the quiz is given in the description below. After answering the quiz, you will be getting the result. So retake the quiz until you find that you have answered all the answers correctly and got the complete out of out results.